In this video we are going to discuss about the discrete version of the Cauchy Schwarz inequality, where at the left hand side we have sum from 1 to n, and this sum of the product in modulus of alpha k and beta k. K runs from 1 to n, and on the right hand side we just have the product of these two sums. We have the sum from 1 to n modulus ak square, the square root, times the sum from 1 to n beta k square, square root. As we mentioned in the previous video about the integral form of the Cauchy Schwarz inequality, the approach will be similar. So we will define a function. Let's define a function. Let's say g of lambda equal to the sum from k1 to n alpha k of lambda plus beta k square. We expand this bracket here. This should be ak squared lambda squared plus 2 times lambda alpha k times beta k plus beta k squared. Let's put the brackets. Okay, when we have the sum of this quantity, we can break it into various different sums. So it will be the sum of ak squared times lambda squared plus the sum k equal to from 1 to n 2 times lambda alpha k beta k plus the sum from 1 to n of beta k squared. Now this can be written as lambda squared times sum from 1 to n alpha k squared plus 2 lambda sum from 1 to n alpha k beta k plus the sum from 1 to n of beta k squared. What is this? This is a polynomial function. It's a quadratic polynomial, and this could be greater or equal to 0. This quantity here, we started from this. By definition, this is greater or equal to 0. Well, assume that we take this polynomial equal to 0. So in order to examine the sign, we need the discriminant. So if the discriminant is a positive quantity, then we have two distinct roots, the two real distinct roots. If the discriminant is negative, we don't have any real roots, and if the discriminant is 0, we just have one double root. Now here the discriminant delta is 2 times the sum from 1 to n alpha k beta k squared minus 4 times the sum k equal to 1 up to n alpha k squared times sum from 1 to n beta k squared. This less or equal than 0. Now this is 4 times the sum squared this term goes to the other side. the product of the two sums. We can cancel out the 4 which appears on both sides. Sorry, it's this. We have cancelled out this, so we just have the sums, the product of the two sums. Let's take the square root on both sides. We have the modulus of the sum of the product of these coefficients alpha k and beta k. And this can be written as the sum from 1 to n modulus alpha k times modulus beta k, and the right hand side remains the same. And there we go, the proof is completed. The idea and the approach is similar to the approach that was used when we proved the integral form of the Cauchy Schwarz inequality, but just we do have the sums, and we don't have these functions, we just have these coefficients alpha k and beta k. So we just define this function of lambda g of lambda, and this is sum from 1 to n alpha k times lambda plus beta k squared. This is a positive function. Now we expand this bracket and we can split the sum into various sums, and we conclude that this is just a polynomial function of degree 2 polynomial, and the variable of this polynomial is lambda. This should be greater or equal to 0, but we have to go to the discriminant to examine when the discriminant is less or equal to 0. We do some calculations, we cancel out the 4s that appear on both sides. Then in this inequality we just take the square root, and we end up with the discrete version of the Cauchy Schwarz inequality. This is also one of the most important and really significant inequalities that are widely used, that are extensively used, especially when you read research papers or when you read the literature to prove inequalities. Cauchy Schwarz is a must. And also there are other types of inequalities like Holter-Minkowski inequality, but I think I have showed the Cauchy Schwarz inequality. Maybe I will make an additional video about the other inequalities, I don't know. I hope that this video was useful for you, and I hope that you have a great day. Thank you in advance, and I wish you the best.